In this video, we're going to talk about what it means to be a linear function. Now, we're not really so much interested in the linear part. Primarily, what I want to talk about is being a function, and we'll mention a little bit about what it means to be a linear function. But let's start with the idea of being a function. A function is like a machine, and what it does is it takes an input value and it changes it around it using multiplication or addition or something like that, and it spits out a new value for your output. And there's one criteria that has to be satisfied for a function. The function assigns at most one output value for each input value, meaning what it can't do is take in an input value and assign it two different output values. So let's look at an example here. Let's say we had one number that we were going to plug in the function. We're going to stick it in the machine. Maybe we plug in the number 3, and this is in your set of input values. So this would be the input set. Out here would be the output set. And the function will accept the number 3. It'll take in the number 3 and it'll change it. And let's say it spits out the number 6. Okay, so 3 is part of the input values and 6 is part of the output values. And so this is considered a function as long as for every input value it assigns it at most one output value and doesn't assign it two different places. So an example of a function that would do something like this might be y equals 2x, because what happens is it'll take your x value and it'll double it. That's what the function does, is it changes the number. It'll double it and send it to 6. So it'll send 3 to 6, it'll send 4 to 8, it'll send 5 to 10, etc., etc. Right, now we also have some names for these things here. Your input values, typically we call that the domain. The domain are your x values that are plugged into a function. And by the way, let me write that as well. Typically you plug in x values and usually you get y values out. And these outputs, we're going to relabel these as the range. So just remember, domain are your input values and the range are your output values. And we typically use the words domain and range, not the words input and output. Okay, now if your relationship is in fact a function like y equals 2x, if you take any x value and you double it, it's going to send it to one place, just whatever that number is doubled. And so if that's the case, if your relation is a function like this one is, then we're actually going to give it some new notation. Function notation is a notation specifically used for functions where we write f of x instead of the letter y. And this is read in English as f of x. So when we had y equals 2x, as long as this relationship is assigning one y value for every x value and not multiple y values, then we'll take this y out, and to rewrite this in function notation, we'll write f of x equals 2x. And what this means is that the function just depends on x. In other words, if you give me a certain x value, then I can plug it in and get the y value, or the f of x value. So let's come back here to this previous page here. All right, so when we had y equals 2x and we replaced the y with f of x equals 2x because this was a function, then if you want to evaluate that function maybe at a number like 3, then what you would do is you would take this x out right here and you would replace it with a 3. So let's try that. F of 3 would be whatever output you would get from plugging in 3. And sure enough, 2 times 3 is 6. So x is 3 and x is equal to 3, but f of 3 is equal to 6. So you have your input value and then f of x is your output value. All right, now when you're talking about domains and ranges specifically of linear functions, to be honest with you, this is kind of boring. I mean, there's really no other way to say it. The reason is this: if you have a straight line, lines typically go left forever and right forever. They typically extend out in both directions. And so your domain, the x values that you're allowed to plug into the function, is typically all real numbers, because every x value has a y value. Let's try a few. Look at this x value. Does he have a y value? Yes, he does, right here. How about this x value? Does he have a y value? Yes, he does, right here. Every x value you would plug into maps to somewhere on the y-axis. And so the domain would typically be all real numbers. Now let me erase that real quick, and let's talk about the range. The range is also, unfortunately, pretty boring as well, because look at the y values that you get out of a function. Lines typically go up for forever and they go down for forever. So your range is typically all real numbers as well. You get all y values, basically. You get all the y values for your outputs. Now, why don't I say 100% of the time? Why do I say typically then, if this is the case? Well, let's start with the range. There is an example where the range may not always be all real numbers. Think about horizontal lines. Now, I know those are pretty rare. We don't see these a lot, but just think about a horizontal line. The domain for this function would be all real numbers, as it typically is, because you could plug in any x value and get a y value. Let's say this y value is maybe 4, let's say. But how many different y values are you going to get out of the function? Just one. You just get 4. You never get 5, you never get 6, you never get 7, because it's horizontal. Now, if it was even the slightest bit tilted, eventually it would go up to infinity and down to negative infinity. But if it's perfectly horizontal, the range would not be all real numbers. It would just be 4, or whatever the case may be. Now, if you're looking for a case where the domain is not all real numbers, that's a little tricky, because you could think of a similar scenario with a vertical line that might restrict your domain, but we have to be a little careful here, because if you have a vertical line, let's say at -3, for example, this actually isn't a function at all. This isn't a function at all. Now, why? Because as I said earlier, most lines do represent functions. Why don't vertical lines represent functions? Well, it goes back to a subtle detail that we mentioned earlier. You remember how we said a function has to assign at most one output value for each input value? Vertical lines don't play by those rules. Think about it. List off some points on this this vertical line right here. Maybe -3, 1, and maybe -3, 2, and maybe -3, 3. Well, look at this. -3 is your input value, but yet we're sending it to 1 and 2 and 3. We're sending it to multiple output values, which is not allowed. Functions are supposed to assign at most one output value. So here's I guess a good rule of thumb. Every linear equation is represented by a function except for vertical lines. But as long as it's not vertical, even if it's horizontal, that will be considered a function. All right, now there's a lot more I can say about functions, specifically linear functions. We need to talk about how to evaluate linear functions, how to graph linear functions, and all those good things. But just for the sake of keeping this video short, we'll just end it with this. A linear function looks like f of x specifically equal to mx plus b. You can really have functions that have anything on the right hand side. X squared, the square root of x. The only thing is that those functions are not linear. But if it looks like basically y equals mx plus b, then it'll be considered a linear function. And so in the next video, we'll talk about how to evaluate these guys. And that means plug numbers into your function. And we'll talk also in another video on how we graph linear functions like this.